So first of all, we have to look at the basic concept of experiment. After all, probability is basically an assignment of value to certain outcomes of experiment. So first of all, we would like to see what is an experiment. We will give a generalized description saying that an experiment is nothing but an activity that generates outcomes. Okay. For example, if you toss a coin, that's an activity. So you get either head or tail, that's an outcome, right? So this experiment has two outcomes. Similarly, if you toss a die, you will get 6 outcomes. If you measure a temperature in a room, you may get an infinity of outcomes. So in each case, you are carrying out an activity, and that activity is resulting in something which we call an outcome of the experiment. Right? In this case, the value of the temperature. And there may be a number of outcomes of an experiment. That number may be finite, it may be countably infinite, or it may be uncountably infinite. There is a distinction between countable infinity and uncountable infinity. For example, the number of integers are countably infinite. It is an infinite set, but you can still count them. While the number of reals are uncountably infinite, because if you take any two reals, between those two reals you will again get an infinite number of reals. So therefore it's actually a higher order of infinity, right? So in our case, we are now taking a rather generalized view of probability than what we probably learned in school. So we have to encompass, since we are mainly going to be dealing with real variables, so we have to deal with experiments which throw an infinity, possibly an uncountable infinity of outcomes, right? So example could be coin tossing or die throwing, whatever. Now, a single performance of an experiment is generally called a trial. So you can perform any number of trials of that experiment. If you measure the temperature on 7 days, you have performed 7 trials. Right? That's a trial. Now we come to an event. An event is actually a slightly more complex entity than an outcome. Right? It's actually a generalized entity. For example, if you throw a die, right, there are how many outcomes possible? Distinct possible outcomes? 6. Right? But at the same time, you can, of these 6, you can define another outcome or event, saying that in this case, suppose you define that the face that comes up is going to be even. So if you define it that way, then this event, which says that if you throw a die, the outcome is that the face that comes up is going to be even, is 2, 4 and 6. So it is now an event which consists of a set of outcomes. Okay? So in general, an outcome may not be the lowest level things that can happen. It can also be subsets of possible outcomes or events. So basically events are sets of outcomes. And sometimes we say that outcomes are outcomes are elementary events. We can also say that. Elementary events. So they are the set of distinct things that can happen. Right? So this is terminology. So now, having understood the basic concept of an experiment, let us see the definitions of probability. We learned a definition which we in school, okay, which said that if you perform n trials of an experiment, and if you are interested in an event A, right, and if out of those n trials there are a number of cases where A occurs, then probability of A is defined as limit of n tending to infinity Na by n. That is the relative frequency of occurrence of an event generally we say in a large number of trials, right? So if you toss a coin, we say that if you have a fair coin, then the probability of a head occurring is 0.5. Now, does it mean that if you toss a coin twice, you will get one head and one tail? No. So it is expected that that if you go on tossing the coin in a fair manner, then for very large n, this n head by total number of tosses will approach 0.5. This is an idea, right? So this is what is known as the so-called the relative frequency definition of convention. This is called the relative frequency, Na by n. Now, one good thing about this definition is that it gives a sense of probability. That it is actually, how many times something that we are looking for is occurring. That gives our intuitive physical sense of probability. That's a good thing. But at the same time, mathematicians are very, very abstract and logical people who do not care too much for physical cases. So they would say that no. What is this? First of all, what is the use of this definition? Because if you are talking about physics, can you really verify this limit? You cannot, because then you have to do an infinite number of trials. And then without performing an infinite number of trials, how do you know even that this limit exists? You don't know. So anyway, you are making a hypothesis that if you perform an infinite number of trials, this quantity Na by n will approach a limit. This is your hypothesis. You cannot verify. So based on that hypothesis, you are defining this probability. So they would say that no, why all this? Let us not assign any. Let us not find out that is how we are assigning these numbers p. But let us say that if we assign if we define a function probability by which we will assign some numbers to some events, then what should be the properties that these numbers obey? Then whether you assign these numbers based on your belief or whether you assign the numbers actually by doing a large number of experiments, that is immaterial. But if you want to assign a sense of probabilities and then base a logical deduction system on that, then this definition should obey certain what are known as axioms. So any assignment, how you have done that assignment, whether you knew it or whether you heard it or whether you found it in your experience, that is immaterial. But if you define those numbers, then they must be defined following some rules. And any number and any assignment scheme which obeys those rules is a valid probability assignment. Okay? Without knowing too much about how you arrived at it. So they are not interested in that. In fact, if you read modern books on probability, people widely argue that this is the more elegant and better way of defining probability rather than on relative frequency. Okay? So here comes the axiomatic definition. It is called axiomatic because it is a definition which has to satisfy certain axioms. Okay? So before defining that, people generally define what is known as a probability space. Don't get intimidated by terms. They are really simple quantities. Only mathematicians are very rigorous, so they would like to give terms to everything and would leave nothing unstated and things like that. So it sounds a bit complicated, but it makes sense intuitively. So first of all, they will define a set called S, which is the set of all possible outcomes. So if you toss a coin, this S is going to be 1, 2, 3, 4, 5, 6. 1, so for tossing a coin, this set is going to be 1, 2, 3, not coin, 5 and 6. This is your set S. Okay? And events are all subsets of S, including the null set. That is, if you take, so what do you mean by all subsets of S? You get something like the null set, or then you have all 1, 2 and so on, and then you have all 1, 2, 2, 3, or 1, 3, and then you have 1, 2, 3. So all subsets of S, including S itself. All of them are possible events, right? S is generally called a certain event, because what is the meaning of an event? When you say 1, 2, what is the event? The event is that either a 1 or a 2 occurs. If a 1 or 2 occurs, then we say that this particular event has occurred. So obviously S is called the certain event because S contains all outcomes, so it must occur. And phi is called the impossible event, because if you toss a die, one of them will come, so the empty set cannot come. Therefore, it's the impossible event. Remember that. Okay. By terminology, it is the impossible event, and these are the elementary events. Okay. So now, what is the probability? Probability is simply defined as a mapping. So it is a mapping from 2 to the power S. 2 to the power S is again a notation. It means it means nothing but all subsets of S. It is the set of all subsets of S. It is called the power set of S. So it is a mapping from the set of all subsets of S to the interval 0, 1. What does it mean? That means if you take any subset of S, suppose I say that a number y equal to fx is a mapping from reals to reals. What does it mean? It means that if you choose a real x, through the mapping you can get another real y. Right? So in this case, this is the domain of the function. That means if you choose any subset of S, then that subset you can assign a value which must lie between the on the real line. It is the closed interval 0 and 1. So it has to be assigned a value between 0 and 1, such that you cannot assign it in any way you like, such that for all events A, this assignment must be greater than or equal to 0, because it is assigned 0 and 1. So it is trivially satisfied if you consider it as a mapping between 0 and 1. So the probability of an event cannot be negative. It must be greater than or equal to 0. Secondly, you must assign it in such a manner that the probability of S must be 1. That must be followed. You cannot make any other assignment for the event S. And if you have two events such that their intersection is null, that is, they are exclusive events. For example, one event is 1 or 2 occurs, another event is 3 or 4 occurs. These are exclusive events. If they are exclusive events, then the probability of A union B, it must be the sum of probability of A plus probability of B. You must assign numbers to these sets in such a manner. These three axioms must be satisfied, and any assignment of a function which satisfies these three is a valid probability assignment. Then after satisfying these three, how you exactly assign numbers to these sets is actually your business. You can do it on various things, right? So, and well, this result is actually extendable for a countable infinity of sets. That is, if you have mutually exclusive sets A1, A2 up to AN, countably, if I not AN, A1, A2, dot dot dot, countable exclusive sets, then probability of A1 union A2 union dot 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 is probability of A1 plus probability of A2 and so on. So this result, which I have stated for two sets for simplicity, can be extended for a countable union of sets, but not for an uncountable. These are very subtle. There are some very subtle mathematical details which I will skip, which I will not even mention, because they will require some understanding of things, especially DR analysis. I mean, you have to know what are open sets, what are closed sets, what is their convergence, what is uncountable union, countable union. So they are actually very technical matters. So, and they hardly ever matter. So some of those things I will gloss over. If you are really interested, you should read a rigorous book on probability. So this is just for mentioning, because after all we are interested in probability spaces which have an infinite number of outcomes. So we have to always keep track of this. Now, incidentally, the conventional definition of probability based on relative frequency satisfies the axioms. For example, Na by n is greater than 0, because Na is greater than or equal to 0 and n is greater than 0. So therefore Na by n must be greater than or equal to 0, right? Na is greater than or equal to 0 and n is greater than 0. So therefore the relative frequency definition satisfies the first axiom. Obviously, if for the total set S, n is equal to n, because any time you try, S is going to be satisfied. So therefore n is by n equal to 1. So the second axiom is also satisfied. Similarly, you will find that if the events are exclusive, then n of A union B is nothing but Na plus Nb, because there is no common. A and B cannot occur together. So therefore n A union B by n is simply equal to Na by n plus Nb by n. So this is probability of A, probability of B. So the relative frequency definition is just one of such probability assignments. There could be an infinite number of other ways of assigning probability to events. But the relative frequency definition which we studied in school happens to satisfy the axioms, right? So it's a generalization actually. Okay. Similarly, we sometimes will come to this thing that two events, if they are equal, obviously probability of A will be equal to probability of B, because it's a function, right? But probability of A equal to probability of B never implies that A is equal to B. Obviously, probability of 1 and 2 and probability of 3 and 4 are same. Doesn't mean that the set 1 and 2 is equal to the set 3 and 4. No question. But you can have a set, you can have two sets which are equal only in the sense of probability. So you can say that they are equal with probability 1. Right? What does it mean? It means that the probability of, say, you have learned about Venn diagrams. So this is A and this is B, right? So what is A union B? A union B is what is A union B minus A intersection B? It is this one. Right? So if the so this is another event because it's a set. So if the probability of this is 0, then the two events are supposed to be equal with probability 1. Means what? Means that the event set may occur, that is the set A and the set B are actually different. I mean, as they have been defined, they are different. But these events cannot occur because the probability of this hash part is 0. which means that these events cannot occur. Only this part can occur. So if these events cannot occur, as far as probability is concerned, the set A and B are equal. Are you following?
No.
What I am saying is that, see, the A and B obviously are different sets as they look, they are not same. So how they are different? They are actually different in this part, because these are the elements which occur in A but do not occur in B. Similarly, these are the elements which occur in B but do not occur in B. Now, if the probability of these events are 0, it means that these elements where the set A and B actually differ from each other, they do not occur. They have probability 0. So only this part occurs which is common to A and B. So as far as the probabilistic condition is concerned, A and B sets are equal. So it is equal with probability 1. It is equal in the sense of probability. They are not equal as such. Right? So now the thing is that if you come to infinite sets, then we will find that we have seen that how can you define a probability? You can define, for example, if you have a set A is equal to 1, 2, 3, then you can define PA is equal to P1 plus P2 because they are mutually exclusive events plus P3. Right? So in this way, you can assign probability to elementary events and simply add them up. You will get the probability of the event. Right? But the point is that when can you do it? Can I do it in all cases? For example, if your probability space is the real line, then can you do it?
No.
I mean, it turns out that these are some mathematical details. It turns out that the assignment of probability actually cannot be done to all subsets of points in the real line. This is why mathematicians are great. That is, they have been able to find out that there are some weird combination of points you can take on the real line on which you cannot define probability. So that's why they will try to circumvent this problem, and they will not define probability of elementary events. Okay, that's why when you have the real line, you don't define probability of a point. It's not defined. What is only defined is probability of intervals. Now intervals are always sets of points, right? So how do we define probability for the when my probability space is real line? Let us say you can easily extend it to multiple dimensional space. Real line is one dimensional space. Okay. So how do you do that? You first define a function called alpha x for any value of x such that it is greater than 0, and integral of minus infinity to infinity alpha x dx is 1. That is, if you integrate the function alpha over the real line from minus infinity to plus infinity, it will be 1. And then once you have defined this function, then you define probability in this fashion. You say that the probability of x is less than or equal to xi. The probability that a value, if I measure the temperature of this room, the probability that it will be less than 25 degrees centigrade is. Okay? So we can, on the real line, we can only make such statements. We cannot make a statement that what is the probability that the temperature of this room is going to be 25.000000. This statement actually mathematically does not make sense. So you can say what makes sense is what is the probability that the temperature is going to be between 25 and 25.001. That makes sense. But what is the probability that the temperature is going to be 25.00 is not a well posed thing. So what they say, so you define probability like this, that you We find probability x less than or equal to xi is minus infinity to xi of alpha x dx. This is how it is defined. This is how the probability is defined. So now, and if you define what is the probability that x is less than or equal to x2 and greater than or equal to x1, that is, this is x1, this is x2. So what is the probability that if you perform an experiment or a trial, the outcome of x is going to be a value in this range? That is integral of x1 to x2 alpha x dx. You integrate the function alpha x from x1 to x2. Obviously, because when x is less than or equal to xi, it means x is greater than or equal to minus infinity, less than or equal to xi. So when you have, so you can actually cast this in this form, right? So you define probability in terms of integrals, and therefore this function is called a probability density function. So the functions that you see, for example, the normal distribution, they are all probability density functions. If you want to have a probability of a normal variable, you will have to integrate the normal distribution. Then you will get the probability that a normally distributed variable is going to be less than something, or right. And you can also define other kinds of intervals. For example, you can take an union of such intervals. If you want to define that what is the probability that x is greater than 2. So you take what is the probability that x is less than or equal to 2. So 1 minus that will be the probability that x will be greater than 2. So you can define all kinds of subsets which may be joined, which may be separate, all kinds of things using this definition. And you may also like to verify that whether it satisfies the axiom. Any definition of probability that you make must satisfy those axioms.
So why are we taking the interval from minus infinity to 0?
That's because, actually suppose we take the case of measurement of the temperature. Why should we consider minus infinity? I mean, after all, especially for temperature, there is nothing called minus infinity. It is minus 273 point something. So even physically, it is not minus infinity. So in such a case, you can always assume, see, this is a generalized definition, you can always assume that alpha x is equal to 0 for all x less than minus 273. So you start your alpha function, if you want to, even if you want to take a finite range, you need not, and practically speaking you need not. But if you want to deal with a finite range, simply make the function alpha 0 beyond that range. That will do. You understand what I am saying? So
why can't we take minus infinity to plus infinity?
No, minus infinity to plus infinity is 1. That means, what are we trying to say? If you take minus infinity to plus infinity, that means you are saying that what is the probability that x is less than or equal to plus infinity? Suppose you put plus infinity here. What does it mean? It means that what is the probability that x is less than or equal to plus infinity? So since x is a real variable, it is always going to be less than or equal to plus infinity. So its probability is 1. That's how we have defined, so that this is satisfied, we have chosen the alpha function such that this happens. Right? So the integral under the normal curve must evaluate to 1 from minus infinity to plus infinity. Right? So now we come to the case of, a very interesting case of conditional probability. Okay? That is, the whole idea is that when we evaluate probabilities of variables, they may differ if we somehow have prior information about other things in its environment. Right? So this notation says that A is an event and M is another event of my probability space. Now, what is the probability of A given that M has occurred? So you are told. So what is the probability of rain on a given day at Kharagpur? You will say, maybe you will say 0.3 something. That is, you for a large number of years you say, you see the number of days it rains in Kharagpur. Now if I tell you that what is the probability of rain given that it is the month of July? Once you are given that it is the month of July, the probability of rain on a given day in Kharagpur changes. Right? So that is conditional probability. So the probability of an event A conditioned on another event M. Right? And because whenever we evaluate probabilities of events, we should exploit all the information that we have already about other events, and then we will be able to obtain the best judgment about this probability, right? So the conditional probability of A given M is defined as probability of A intersection M and probability divided by probability of M. Why? Why is this definition? Because after all, what is the probability of, say, let's take our example. So probability of it being the month of July and it raining in Kharagpur. Suppose M is the probability that it is the month of July. And of course, I don't know whether we should say what is the probability that it is the month of July. So, but anyway, we are just taking, okay, let's take this example. This is that, suppose there are, I didn't write that example. Suppose we have a two-child family. We consider two-child families. Okay. So, what is the probability that both the children are daughters? One-fourth. Right? So, obviously, because what is my sample space? It is SS, sorry, okay, I'll write BB, GG, BG and GB. These are the events that can occur. Now, of this, what is A? A is BB. Now, from this, how can we say that it is 1/4?
1/4.
Yes, he's saying 1/4. Why is he saying 1/4? Have we yet made any probability assignment from the set of samples, from the set of events to the real line? We have not yet made. So when he says 1/4, he is actually making an assumption. He is making an assumption that the probability of a boy or a girl being born is actually the same, and they are independent events. He is making that assumption. Under that assumption, only this probability is, that is, these four events are all equally likely, that he is assuming. That is why he is saying that it is 1/4. Right? So, fine, I mean, we often make that assumption that they are equally likely. So, if it is equally likely, then it is 1/4. Now, what is the probability that you will get both daughters given that you already have a daughter? Given that the first child is a daughter, what is the probability that you will get two daughters? Half. Now, let us see. So, probability of A given B. Now, what is the probability that you have, that the first child is a daughter? What is that set? It is GG and GB. This is the event that the first child is a daughter. What is the probability of this event? Half. So now we can say that what is the probability of A given C? It is probability of no, we are talking about GG. Sorry, if you are right, if you have this, no, we are talking about GG, right? So what is the probability of A given C? So it is what? It is 1/4 divided by half is equal to half. So the probability of getting two daughters, given that you already have one daughter, is half, as we said. Right? So it's interesting to see that now you see that now we come back to our so this is the sense of conditional probability. Right? We are trying to utilize other information that is occurring. So now, for example, now you have immediately have certain results that if M is a subset of A, then probability of A given M is 1. Can you see that? If M is a subset of A, then probability of A given M is 1. Because if M has happened, then already one of A has occurred. So once you are told that M has happened, the case A itself has been satisfied. So there is no uncertainty about it. On the other hand, if A is a subset of M, then M has happened does not mean that A has happened. There can be some event. There is also this possibility that something in M has occurred, but that's not in A. So in that case, probability of A given M is probability of A by probability of M. Why it is probability of A and probability by M? Because it is supposed to be this. So why it is probability of A? Because subset. If A is a subset of M, then A intersection M is A. So probability of A by probability of M. Note that it is greater than or equal to probability of A, because probability of M must be less than or equal to 1. So you see that by incorporation of this additional information that M has occurred, the probability of A that you are now computing has increased. Right? So if you already know that some part of it has occurred, then the probability of the overall event A occurring increases. Right? So and of course you can always verify that conditional probability mapping, this probability mapping, also satisfies the axioms. Again, because why? Again, probability of A given M is obviously greater than or equal to 0. Right? First of all, note that this is defined if probability of M is not equal to 0. If probability M is equal to 0, this probability of A given M is undefined. So you cannot talk about probability of A given M when probability of M is 0, because it makes no sense. Right? So therefore obviously probability of A by M greater than or equal to 0. And probability of S upon M is 1. Why? Because all subsets, because M will necessarily be a subset of S for all, whatever M is. So it is 1. So that is satisfied. And probability of A union B given M is probability of A given M plus probability of B given M. Why? Because probability of A union B given M, let's just work out, is equal to what? Is equal to probability of A union B intersection M divided by probability of M is equal to what? Is equal to probability of A intersection M union B intersection M by probability of M. Now since A and B are mutually exclusive events, So therefore A intersection M and B intersection M are also exclusive events. So therefore probability of A intersection M union B intersection M is probability of A intersection M plus probability of B intersection M by probability of M. So it is equal to probability of A intersection M by probability of M plus probability of B intersection M by probability of M, which is this. So you see that this conditional probability mapping is itself a probability. It satisfies the axioms. Whenever you make a new way of defining probability, it must map the axioms, right? So that is that. Now we have what we call, there are two very interesting theorems. One theorem is called the total probability theorem. So total probability theorem says that probability of, if you have an event B and if you have a partitioning of S. What does it mean by partitioning of S? Means that you have sets A1 up to say AN such that A1 intersection, rather AI intersection AJ is null whenever I is not equal to J, and union of AI is equal to S over all I. What does it mean? That if you, each sets are disjoint, so AI intersection AJ is the null set. There is no common element between these sets, and if you take all the sets together, it will make the set S. If you take union of the sets, you will get the set. So such a thing is called a partition. So if you have a B, any event B, and a partitioning of the set A, then you can write that probability of B is equal to probability of B given A1 into probability of A1 plus probability of B given A2, probability of A2 plus, in the finite case you can write probability of B given AN into probability of AN. This is called the total probability theorem. It's rather simple to prove, because what is this after all? This is probability of B intersection A1. Similarly, plus probability of B intersection A2. Right? Now, since these are disjoint, so you can write it is probability of B intersection union AI, because they are disjoint A1 A2. So whenever they are disjoint, you can take union here, because this plus becomes union of the set, right? Is equal to P of B intersection S, because union AI is S, is equal to probability of B, because B intersection S is nothing but B. So this is the total probability theorem, and based on that, and we'll end here today because you have another class, we have the celebrated Bayes theorem, which says that probability of A given B is nothing but probability of B given A into probability of A divided by probability of B. So you can also write it as probability of B given A into probability of A plus, I mean, if you have, instead of A, if you have for example, if you have n number of A's, then probability of AI given B can be written as probability of B given AI into probability of AI. No. probability of A given. What time is your class? 11:30 you have a class. Huh? Okay. So okay, we'll do that. This is the base theorem for two variables. So see that with this theorem I am able to calculate probability of A given B in terms of probability of B given A. This is rather useful. I mean, you are taking one to the other side. This theorem is widely used in various contexts of probability. So we will stop here today. So we basically reviewed some elementary concepts of probability, and I tried to give you the basic framework in which probability is discussed for infinite and finite